This is a presentation about Swarm-SecOps, a managed cybersecurity service from IP Performance that provides scalable network security.
We have developed and built a number of centralized logging and monitoring platforms with our customers in the education and transport spaces. They needed to understand what was happening on their networks and be able to detect security issues. They faced a number of challenges that were hard to address with traditional tools. These included a large number of users and a high throughput core, which made full coverage expensive with traditional tools. An unsegmented network where malicious actors could easily spread once inside the perimeter. A lot of BYOD student devices, which means no ability to install agents or any security software. Disparate security appliances that are unlinked, making investigation time-consuming and tricky. And finally, a large amount of traffic and logs to process. This made it very expensive to gain full visibility of the entire network with traditional vendors. We broke these down into three key areas that needed to be addressed. Number one was visibility, collecting and curating quality data from the right systems that will provide greater insight for investigations and incidents. Number two was scalability, the ability to scale the infrastructure to cover the entire environment, not choosing which is the most important to record due to limited resources. And finally, technology, understanding and integrating different tools together to ensure that attacks can be identified and remediated. So how does the system work? The first stage is about collecting data from the environment. If you do not proactively collect and store this data, you will find yourself at a loss when questions need answering during a security incident. We decided to use inexpensive sensors to collect metadata from the network and endpoints. We also collect more traditional logs from existing security appliances. Once we have collected the data, we then ship that data to the analysis nodes. The next stage is to understand what we have collected, curate it, and identify any gaps that need filling. We can now start to understand this data set. Baselining requires understanding what your systems do or what is normal for your environment. This stage can include collecting more data or rationalizing duplicates. We can write rules about things we expect to happen and what we expect not to happen. Once we have a baseline, we're then able to identify abnormalities in operations. Finally, we start to hunt for threats. This analysis should be looking for adversary tactics, techniques, and procedures to identify issues, as well as the more easily identified indicators of compromise, file hashes, bad domain names, and malicious URLs. We also have a mechanism to manage and maintain the collection infrastructure simply and easily. Our sensors sit on the network at each significant site and are sent copies of all packets either by a tap or a span port. We build our sensors from commodity hardware and run open source tools on them for network traffic analysis. We have different sizes of unit which are sized for the expected traffic at that capture point. Our largest sensors can currently capture up to 10 gig full duplex, but we are looking to increase this. We've taken an approach of continuously logging all traffic for further analysis, but also looking for known attacks as soon as they are seen. The sensors quietly and unobtrusively observe network traffic, interpret what it sees, and create compact, high-fidelity transaction logs. These logs include not only a record of every connection seen on the wire, but also application layer information like HTTP sessions where they request URIs, key headers, MIME types, and server responses. We also look at DNS requests and replies, SSL certificates seen, key content of SMTP sessions, and much more. The sensor also runs an IDS, which inspects the network traffic for known attack types. We install agents on Windows to collect and ship application, system, security, and sysmon logs. The agent on Linux is used to collect and ship the syslog, application, and audit logs from the system. The analytics cluster is a set of virtual machines that perform different functions. The logs are shipped from the network and are received by the ingest node. They are processed here and normalized into a decent structure. The data is enriched in a number of ways, including threat intelligence and internal GeoIP information. The ingest node then writes this to the search and analytics nodes where it is indexed and stored. The structured data is replicated across the cluster. The visualization node is where the CMAP runs. The CMAP contains detection rules looking for attacks and anomalies. The CMAP can also trigger alerts if detection rules fire. The visualization node connects to the search and analytics nodes to perform searches on the indexed data, and helpful dashboards can also be created to look at the collected data in different ways. The analytics cluster is very scalable. If more resources are needed, extra virtual machines can be added into the cluster very simply. If more compute nodes are needed, These can also be easily added to the hypervisor platform. While it is possible to run the whole stack in the cloud, we have found that the costs can add up very quickly when compared with running on-premises appliances for the same capabilities. So how does this look when we deployed it? The college network looks fairly standard. They have 3 large campuses and a number of smaller ones. The larger campuses are connected together by dark fiber and run at speeds of 10 gig. The larger sites have a mixture of client and server VLANs with users connecting from desktops and mobile devices. They currently have 2 Wi-Fi systems with Eduroam on all sites. We installed our compute nodes at Campus 1. These are powerful commodity servers with lots of memory and a mix of SSD and SAS spinning disks. They run an open source hypervisor. We then run our build playbooks and set up our analysis node cluster on top of the hypervisor. Next, we installed our north-south 10 gig sensor. A fiber tap was installed between the edge firewall and core switch to feed traffic to it. We installed another fiber tap behind the WAN edge router at Campus 1. Traffic from this tap is copied to the east-west sensor. Host agents have been pushed to all college servers and endpoints. This is mainly being done by the college's SCCM server. The config on the edge firewall and wireless LAN controllers is updated to forward logs to the analysis nodes. Network metadata from the sensors, network and security appliance logs, server and endpoint logs are then forwarded to the analysis nodes for ingest, normalization, enrichment, and storage. Now we've collected the data, we can start to check it for quality, find data types that are missing, and use it during investigations. Our next project milestone is to add further analysis capabilities to our analysis nodes. This will look for traffic patterns related to command and control beaconing, strobing, and DNS exfiltration.
Our SOC Lite service has been designed to help our customers run their security operations. A good security operation requires tools to collect data, people to analyse the data, and processes for dealing with these findings. Our service is modular, dependent on our customers' capability and maturity. Our modules cover various aspects of work performed by a security operations center. Build is our base module and involves us building and maintaining the platform. Collect means we work with our customers to understand their context, identify what types of data needs to be collected, and ensure it is ingested into the platform in a suitable format. The detect module covers our team baselining the alerts rule set, enriching the data collected, and triaging SIEM alerts that have been raised. Our final module is respond. This entails us investigating threats, determining if they are true positives, and advising our customers on the actions they should take.